So hi everyone, welcome once more to the channel. So today we're going to look at oscillation, what we call bifilar oscillation. It's a kind of oscillation whereby you suspend a meter rule between two rotor stands, then keep a mass at the middle of the meter rule, and then set it into vertical oscillations. Then take your time, take your period, and take the square of the time. You maintain a constant length for each experiment. So the length we're maintaining here are lengths of 40 cm, 50 cm, 60, 70, and 80. This height represents the length of the trays that are holding or suspend the meter rule. So let's go to the question and then move to the experiment, please. So we have the question, bifilar suspension, otherwise known as torsional oscillation. So you can see two rotor stands there, clamped at 10 cm. Okay, the meter rule clamped at 10 cm and at 90 cm respectively. The meter rule is AB. Then the distance between the two strings is written as D. The distance between the two strings D should be 90 minus 10. That will give us 80. So D is 80 cm. So go to the question, we'll say you are provided with 2 meter rules and other necessary apparatus. 1. Place one of the rules on a knife edge and determine its center of gravity, C. Mark this position with a piece of chalk. 2. Or II, read and record the mass MR of the meter rule. Number 3. Or III, attach the mass 100 grams firmly to the rule AB as C using sellotape. That's C, the center of gravity. IV, suspend the meter rule by 2 parallel threads of length H equal to 40 cm, each at the 10 cm and 90 cm mass respectively. Ensure that the graduated face of the meter rule is facing upwards. V. Set AB, the rule AB, into a small angular oscillation about the vertical axis through its center of gravity. VI. Determine the time T for 20 complete oscillations. Evaluate the period capital T and then T squared. Read and record the distance small d in meters. The small d, as I said, is 80, that is 90 minus 10, 80 cm. Then VII, keeping the small d constant throughout the experiment. Repeat the procedure for other values of H, 50 cm, 60, 70, and 80 cm. In each case, determine the corresponding values of small t, that is time, capital T period, and T squared. Tabulate the readings. Plot a graph of T squared, that is period square on the vertical axis, and H on the horizontal axis. S, determine the slope S of the graph and evaluate S over Q, where A is equal to 2 all over 2 SD squared. SI, state two precautions taken to ensure accurate results. SI, define the time couple as relates to rotational oscillating motion systems. Then SII, give 2 practical applications of a couple in everyday life. So we're going to start the experiment now. So we have the meter rule, and we already determined the center of gravity as 50. At 50, which is written on the board, C, which is 50.0 cm. The length of the thread from here to there is 40. Also from here to there is also 40 cm. So the first serial number 1, the first element H is 40 cm. So we're going to set this meter rule into oscillation. That is, you have to display it slightly. So, and then allow it to undergo 20 oscillations. So let's do that. 1, 2, ready, go. On your stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, what time do you have there?
25.32.
25.32 seconds. So, ask to report 25.32 seconds here. Then, we want to redo it 2 times so that we can get accurate reading. To avoid error, we're going to repeat this one again. Get our T2 and then we'll get the average. So, go back again to start again. Oscillate slightly. And then when you want to do this experiment, all you have to do is close the windows to prevent air interference. So, 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, what the time?
25.38.
25.38 seconds. That is close range. So, to find this value, T, we'll add these 2 and divide by 2. We'll have the average. So, you add these 2 and divide by 2. What do you have?
25.35.
25.35 as the average of these 2. So, we are working with this time now. Then we'll take the period. The period now is this time, 25.35 divided by 20.
1.268.
1.268 to 4sf. Then do T squared.
1.608.
1.608. Okay? So we're going to adjust the tray to get 50 cm length. So the height will be 50 centimeter. Some people now start wondering, how am I counting the oscillation? Because they start wondering, how am I counting 1? I'm looking at this edge. When it moves and comes back here, I count 1. Are you seeing it? So when you go to this place, I'm counting 1. So I'm looking at this edge. Because a couple of oscillation means you have to go there and come back. That is 360 degrees. Okay? You know, when it's any movement here, we're counting 1, 2, 3, 4. I'm watching this edge. It goes there, I take 1. Goes there, I will not count. Returns this place, I'll count under 1, 2, and so on. So we're measuring the length of this thread here, and this is giving us 50 cm. We're giving us 50 cm for the second experiment. So you keep your stopwatch ready, return it to 0, as we now oscillate. So I hold it here, I move it slightly. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So what time do you have?
28.32.
28.32. See, as the length increases, the time will continue to increase. So repeat it to minimize error. Hold it and then displace again slightly. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So what time do you have?
28.38.
28.38. We'll add the 2 of them and then find the average. Divide by 2, add it to divide by 2. What do you have?
28.35.
28.35. Then find the period. Divide this number by 20.
1.418.
1.418. Then square the period. What do you have?
2.010.
010. Okay. So move to the third experiment when the height is 60 cm. So we're about to start the third experiment. The height here is now 60 cm. 60 cm. So we want to oscillate, so keep your time stopwatch ready. Move it slightly. 1, 2, ready. Wait, it says dangling. So it's not, we have to repeat it. So it's not oscillating very well. It's gyrating. So 1, wait. Let me have, okay. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
31.02.
31.02 for 60. Okay. Repeat it again. So we're going to repeat again. Remember that this place is at 10, this place, the trade here is at 90. It's constant. What we are varying is the length only. So, we're gyrating. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
31.08.
At 1.08. Please add and find the average of the two.
31.05.
At 1.05. Divided by 2 into the period.
1.553.
553. Spare the period.
2.412.
2.412. So go to the fourth experiment when the height is 70 cm. So we have to adjust this. So we're about to do the fourth one when the height is maintained at 70 cm now. So we'll oscillate this slight displacement. So keep your time ready. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What do you have?
33.50.
50. So, repeat it again. One, two, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
33.50. 33.58.
33.58. So you add the 2 and find the mean value, the average.
33.54.
3.54. Divide by 20 to find the period.
1.677.
1.677.
77.
Square the period to get this.
2.812.
2.812. So go to the last one when the length is 80 cm. When the height is 80 cm. So the length now is maintained at 80 cm. So we was laid this. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
35.90.
35.9. 35.what?
90.
90. We'll do a second one. One, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
35.80.
35.80. Find the average of these two. You add and divide by 2.
35.85.
5.85. Then divide by 20 by the period. The 5.85 by 20.
1.793.
793. You square 1.793 to find the square of the period.
3.215.
215. So we have come to the end of the experiment. Then the next thing to do now is to plot the graph, find the slope, and then conclude. So the next we're going to do is we're going to find the mass of the meter rule that we use for the experiment. We have to find its mass. And this is the electronic balance. So it's on 0, you can see that. We'll now weigh the meter rule. Making sure the center of gravity is resting on the weighing pan. So it's steady. What the weight there? This is 189 grams. So this meter rule is 189 grams. So we'll report here MR 189.0 grams. That's the mass of our meter rule that we use in the experiment. So we can now go to the graphing. So now move to question IS that says plot a graph of t squared on the vertical axis and h on the horizontal axis. So you have our t square values from the reading on the board. 1.608, the length is 40. 2.010 corresponds to 50 cm. 2.412 corresponds to 60 cm. 2.812 corresponds to 70 cm. 3.215 corresponds to 80 cm. So t squared against h. This is h, not L. H. So we'll now go to the graph. Choose our scale. This is t squared as this. Our scale is, we have a scale of each bus here is 2 cm. So this is 4 cm for 1 unit. And that 4 cm for 1 unit, you can see 1. So each 2 buses for a unit here, 1, 2, 3, 4. So 4 cm to 1 unit on the t squared axis. We'll now go to the h axis. We chose a bus, which is 2 cm for 10 units. So you have 10, 20, 30, 40, 50, up to the last value, which is 80. So having done that, we'll now move. I'm going to plot one decimal to one decimal place. So 1.6 corresponds to 40. We'll locate 1.6. So here is 1, here is 2. So each line is two lines is 0.1. So 1, count 2 lines, this is 1.1, 1.2, 1.3, 1.4, 1.5, and then 1.6 is here. So corresponds to, what number corresponds to 40? So 40 goes with 1.6. That is 1, 2. So that is should be here. So 1.6 go with 40. Then 50 goes with 2, approximately 2. 50 goes with 2. Where is 2 is here. And here is 50. Goes with 2. 60 goes with 2.4. This is 60. We move up. Here is 2. The next 2 lines, tiny line 2.1, 2.2, 2.3, and then 2.4. I'll count again. 2.1, 2.2, 2.3, and then 2.4 should be here. Okay. Then 70 goes to 2.8. 70 goes to 2.8. So the middle here, between 2 and 3, the middle line is 2.5. So 2.6, 2.7, and then 2.8 should be there. Then 80 goes with 3.2. We have 80. This is 3.1. The next 2 lines 3.2. So we have a good graph. We'll now join the points. Let's join the points. So joining the points and getting our best line. So we have about 4 points. 1, 2, 3, 4 on the straight line and 1 point off due to experimental error. So next we'll do is to find the slope. To find the slope, I can take this point here and the 4th point there to find my slope. So I can take it. So find my slope, I'll now write S equal to change on the t squared axis over change on the h axis. So this point here is around 2 point. You can get it from here. Is 2.8. So I have 2.8. Then the lowest point here is around 1 point. That should be 1.6. That is it. Minus 1.6 all over. Move to this side. The corresponding point is 70. I have 70 there. We compare to 2.8. Minus the corresponding point here is 40. 40 compared to 1.6 from the table. So this is in seconds squared. This one is in centimeter. So someone should do 2.8 minus 1.6 for me. 2.8 minus 1.6 will give us, I think, 1.2.
Yes.
Then 70 minus 40, what is it? 30 cm. So S becomes 1.2 seconds squared. Divide the 30 by 100. Let's convert to SI unit. The 30 by 100.
0.3.
0.3 meter. So divide 1.2 by 0.3. 4 seconds square per meter. Alright, since it's 4, we write it as 4.0 seconds square per meter is our slope. We'll now move to the next thing. You say evaluate K equal to S over, this should be S over Q, where Q, this is Q, not A, where Q is 2S, 2 over 2S, so Q is 2 all over 2SD squared. So we have 2 here. What's the slope? 4. Okay, there's another 2 there. 2 times the slope is 4. What's that D, by the way? I did the distance between what? 10 and what? 90. So our D, for the experiment, our D is 90 minus 10, which is what? 80 centimeter. But remember that we kept all this in SI unit. So we convert this 80 to what? To meters. So D becomes 80 over what? 100, which is what? 0.8 meters. So 0.8 here. So this will now have what is this? This is 2 cancels 2. We have what there? 1. 4 times 0.8 give us what? 3.2. So divide 1 by 3.2. 1 by 3.2, what do you have?
0.3125.
0.3125. But we will have worked out the unit of the slope. Because this the unit of this quantity. This is 2. Which of them has the unit here? Slope. What unit of the slope? Slope is what? Seconds squared over meter. Then this is distance now, which is what? Meter what? Squared. So the numerator is dimensionless, has no unit. So you see that 1 meter cancels what? 1 meter. So that should become units now become per meter per second squared at the unit of this Q. We are now obtaining our Q. We are asked to find K equal to S over Q. Our slope is what is our slope? 4.0 seconds squared per meter squared divided by 0.3125 per meter per second squared. So this cancels out. So divide 4 by, is it 12?
12.8.
12.8. So this is per second. Going up becomes second raised power 4. But let's be very sure of this thing we're calculating, so don't make mistake here. So what again? The S is what unit? That's the unit of the slope. Second per meter. And then our D is 1 unit. Meter was squared. So we 1 meter cancel 1 meter. Now have meter second squared under. So that will give you this. So the slope, I think we are right. So whatever it is, so that could be the moment of inertia. Then we'll now go into number SI. Says state 2 precautions taken to ensure accurate results. What precautions do we observe in the experiment? We make sure the precautions should be 1, I made sure that I use a light. I made sure that I use a light inextensible thread. A thread that will not extend, that not elastic. Number 2, I made sure that I displace the meter rule through a small amplitude. You can still say that you made sure you avoided air interference. Then give 2 practical application of a couple in everyday life. So what are the practical application of a couple in everyday life? Turning, opening and closing of tap. Opening of tap. So steering of a car. So these are some of the applications of couple in everyday life. Steering of a car, open and closing of a tap or valve. The movement of the ruders of airplane or ship. Rudder is spelled R-U-D-D-E-R. So these are closing of tap and opening of tap. Movement of the door about its hinges. So these are application of couple in our everyday life. So we have come to the end of this experiment on oscillation, which is termed BIFILAR oscillation. It's the kind of oscillation that obeys simple harmonic motion, especially when it displays the meter rule through a small angle. So we have come to the end of those, please. And then if you are seeing the channel for the first time, subscribe to the channel by tapping on the subscription button under the channels, under the video, and then you can also share the video to someone in need. Thank you.